Good afternoon, everyone. This is Mr. Couple. I'm here today with my IBHL Year 1 students, and we'll be learning about electric resistance. This is picking up from our last lesson on potential difference or electric potential, where we talked about the how that relates to energy, like the field potential is the energy per charge. So we're going to be continuing today talking about this concept called electric resistance. So in this picture down here, we have a conductor. Like this is just some sort of like a wire or some sort of a conducting material, and we've established a potential difference across the ends of that conductor. Maybe this has been connected back to like a battery. The symbol for battery looks like that. Also, I should probably mention you guys in the IB data booklet, you actually have a whole page where they just give you all these symbols for different circuit components. So you can see like a cell looks like that. That's why I drew that symbol there. We could talk about resistors. We'll be talking about resistors on the next lesson. That's the symbol for a lamp. So there's all these different symbols in here that you need to know about. So I would recommend you guys go check these out at some point in the data booklet if you have a copy of it. So imagine, you've got like some like a wire or like a little strip of metal or a lamp or something. That's what this conductor here is, just something. And it's allowing charge to flow through it. So we establish this potential difference across it, maybe by connecting it to the terminals of an electric cell or a battery, and we've got a current flowing through that material. And notice that the current is flowing to the right. Okay, so let me get rid of that. All right, so what we have to imagine is like we're going to look at these things called the lattice atoms. So these big circles here, these are the lattice atoms, or oftentimes we'll call them the lattice ions because they don't have this. What am I trying to say? They've lost an electron, right? Because these electrons here, they used to be part of the atom, but they've been removed. They're kind of slowly or freely flowing through the material, so that we can call these lattice ions. But basically, these are the nucleus or the extra electrons that are on there. Like that's like the leftover atom after the free electron sort of drifts away. So you call that the lattice ion or the lattice atom. An electric field forces the electrons to move through the conductor, i.e., an electric current is created. So by connecting it across a potential difference, we've created an electric field in this region inside the conductor. And so where all these electrons are, there's an electric field there. Now, which direction does the electric field point? This is a question for you guys. What are your thoughts? So notice that the electrons are moving to the left. So what direction does the electric field point?
To the right.
Yeah, the electric field always points the way a positive charge would move. So the electric field is to the right. All the negative charged electrons are moving to the left. Okay, so that's the first thing you guys need to know about is like these electrons are going to be given energy by the electric field. The electric field is going to transfer energy to these electrons, and the electrons are going to start to accelerate. They're going to start to move. But you can imagine, like, look at the structure of these lattice atoms. Like, look at how the atoms in the material are held together. And the other thing to remember is that this is just a static image. But all atoms, when they're bonded together, these are like springs, these bonds. So all atoms, when they're bonded together, these guys are actually like oscillating. These atoms are vibrating all over the place. And so imagine that as these electrons come like whipping past, they're actually going to collide with these lattice atoms. And every time an electron collides with a lattice atom, it's going to lose energy. And so this is what we want to talk about to understand resistance. So this is going to give rise to this idea of resistance. All right, so first up, all of what I just talked about here. So we want to outline the energy transfers involved when an electron moves through this conductor. Let's see, I need my text box tool. Okay. So the first thing we're going to talk about, let's see, insert text. I'll do it in red. Okay, so the first thing I want to talk about, do it right here. I don't want to write because my writing is terrible. I'm going to type. What have I done? Go ahead. Okay, here. So the first thing we want to talk about is that the electrons gain energy from the electric field. So that's the first thing that we know is happening. Okay, and then what happens to the electrons? So they're going to speed up, they're going to gain kinetic energy, they're going to go faster. Then eventually, what is going to happen to those electrons? You guys tell me. So just track an electron. What's eventually going to happen to this guy if it keeps going? Remembering that these atoms are oscillating. So what's eventually going to happen to this electron right here? It's going to keep moving, and then it's going to
It's gonna collide with an atom.
collide with an atom. Is that Chris? What's
Yes.
up? Welcome. Well, thanks for coming, Chris. What did I do here? What am I doing? Okay.
I
I
was
want
eating
to.
lunch, man.
Okay, cool. I want to get back into this text box. Are you going to let me back in? Okay, cool. Let me back in. All right. So eventually what's going to happen is the electrons suffer inelastic collisions with the lattice atoms. I'm going to call them ions with the lattice ions because they're not atoms because the fact that there's free electrons here means that they're no longer part of the atom, so they're not atoms anymore. Atoms is only when there's the same number of protons and electrons. So these are lattice ions. So the electrons suffer inelastic collisions with the lattice ions. So then what's going to happen to the lattice ions? So imagine you've got this lattice ion and here comes an electron, and it plunks into it. What's going to happen to the lattice ion? You guys are quiet. No one?
They gain an electron.
Nope. Keep thinking. The electrons are free to move, so they're not held on to these atoms at all. They're just freely moving all over the place, and they're being pulled by the electric field still. So as soon as that electron goes blunk and bounces off the atom, the electric field is going to keep pulling it, and this whole process is going to start over again. But what will happen if you have like a stationary, let's say you have a stationary atom right here, and an electron comes flying in and whacks and hits it? What's going to happen to the lattice ion?
Move. It'll
It's
move.
going to move. So the lattice ions gain energy and oscillate more rapidly. So what do we say about that? If an atom starts to oscillate more rapidly, what do we say? The material is going to do what? What happens if you take atoms that are like this and you go blunk, 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 and they start to go faster? What does that tell you about the material?
It gets hotter.
Mm-hmm.
Yeah.
The material will increase in temperature. Okay, that's the energy transfers. So the electrons gain energy from the electric field. The electrons suffer inelastic collisions with the lattice ions. The lattice ions gain energy and oscillate more rapidly, and the material will increase in temperature. Now, I'm kind of not giving you the full picture here because what's going to happen now is as soon as the electron loses the energy through its collision, as soon as the electron transfers the energy into the lattice ion, the electron is going to get accelerated again by the electric field. So this whole process is just going to keep repeating over and over again, with the electrons continually pounding and colliding into those lattice ions, raising the temperature of the material. So this is why whenever you have an electronic device, like if you're using a phone and you talk on it for a while, it's going to start to get hot because that's what's happening. When you run charge, when you push a current through a conducting material, the material is going to heat up. It's going to get hotter when you do that. And so that's why you have to install like fans and things like that into your computer hardware to kind of cool it off so it doesn't, overload and melt and get fried. So keep that in mind. So this is we call this a potential difference where the electrons are losing energy when they pass through the material, and it's that loss in energy per unit of charge that's called a potential difference. So the potential difference is very much connected, is exactly this loss in energy. It's just the energy loss per charge that flows through the material. In 1826, the German scientist George Ohm discovered that when the temperature of most metallic conductors is kept constant, so this is really important. So when the temperature is kept constant, what he found was that the current through the conductor was proportional to the potential difference across it. So this is called Ohm's law. So he found that the current through the conductor is proportional to the potential difference across it. This statement is known as Ohm's law. Now here's the thing, it's not really a law, right? Because it just said right there, this isn't always true. So it's not a law because it's not something that's always true. When is the only time that Ohm's law is actually true? This is a question for you guys. When is Ohm's law true? The only time that it applies is when?
Temperature is constant.
Yeah, when the temperature is constant. But not just that, it's most conductors. So not every material is going to obey Ohm's law, and the temperature has to be constant. So Ohm's law is not really a law. It's just something that he saw, like in initial investigations into electricity back in the early 1800s. He saw that for most materials, as long as they don't get too hot, that this is true.
Ohm's guideline.
Yeah, Ohm's guideline. Yeah, Ohm's initial observations. So materials that obey Ohm's law, they're said to be ohmic materials. So if a material is ohmic, you could use Ohm's law if the temperature is constant. But if the material is non-ohmic, and most materials are, then you can't actually use Ohm's law. Okay, so what exactly is Ohm's law? We'll look at this graph. So this graph is called an IV or a VI characteristic graph. And so the idea is that you've got some, material like this, some conductor, and you hook up a potential difference across it, potential difference V, and then you just measure how much current goes through it. So you do this for all different amounts of potential difference. You try 1 volt, you try 2 volts, you try 3 volts. So you just keep increasing the potential difference, just go, crank it up, and then you check to see what current flows in response to that. And you can make this graph. So is this ohmic or non-ohmic? The material that we've, up here, we've connected this potential difference and measured different currents. Is this material ohmic or non-ohmic? What are your thoughts?
Ohmic.
Ohmic.
This is absolutely ohmic. And so what's the telltale sign that this is an ohmic material?
So it's a linear graph.
Yeah, it's linear. So outline why this material is ohmic. It's because it has constant gradient. On the I versus V graph. And so that constant gradient shows that I is directly proportional to V. So what if instead the graph looked like this? What if it was that red line? Would that red line be ohmic?
Nope.
No, and you can see that's because the current and voltage are not directly proportional. And most materials are not ohmic. All right, express Ohm's law as an equation. All right, so what Ohm's law is basically saying is like I is equal to some proportionality constant. I don't know what to call it. I'll just call it a K times V. So we can see that right here. Like this is just the equation of a line, y equals mx plus b. So y being the I, and x being the v, y equals mx. So k is just some proportionality constant. So it turns out that what k is equal to, that k is equal to 1 over this quantity that we call the resistance. So the equation for Ohm's law is I is equal to 1 over R times V. And now why am I writing it in this weird way? Well, because this is the gradient. So I ran out of space on this worksheet, but I could have asked you from this graph, determine the electric resistance of this material. And so the electric resistance would be the reciprocal of this gradient. And I guess I should have done that, but it's not that important. Generally, though, you'll see Ohm's law written as V equals IR. This is how you'll usually see Ohm's law written. You can notice if you just take the R down there and just move it over to the other side, you get V equals IR. But I wanted to show it this way because this is the way that you actually determine whether a material is ohmic or non-ohmic, and then this is how you measure the resistance, is by trying different currents and different voltages, and then determining the gradient will tell you the resistance. If we were in class, I would have had you guys do this lab, but we're not. So let's talk about this thing called electric resistance. So Ohm's law defines electric resistance as the potential difference divided by the current passing through it. Or as it says down here, the electric resistance R of a conductor is defined as the potential difference V across its ends divided by the current I passing through it. Now the units are kind of weird. So normally what you do is you take the last name of the scientist and you capitalize it, and then that's the unit, right? But with ohms, we can't do that because capital O would look like a 0. Imagine if like the resistance was 10 ohms and you wrote it like that, it would look like you wrote 100. So we decide to use the Greek letter omega, which kind of looks like an O, and instead. So the ohm is defined as a volt per ampere. Volt per ampere is what the ohm is. All right, let's do an example problem. A what? 2-slice. Oh, geez, let me fix that. So a 2-slice. Oh, I can actually just. Oh, whoa. I'll just go like this. I wanted it to say a 2-slice bread toaster consumes 850 watts of power when plugged into a 120 volt source. So this is like a normal toaster you'd find in your kitchen. 180 watts, plug it into the wall. The wall is 120 volts. Calculate the current in the toaster. Okay, so we did this. This is just a tie back to last lesson. So 180 watts of power, 120 volts. So the equation to relate power and volts is P equals IV. Power equals current times potential difference. And we know the power, we know the potential difference, we're trying to find the current. So if we want to find the current through the toaster, it's just the power divided by the potential difference. So it's 850 watts divided by 120 volts. So the current is the watt per volt. So the current is 850 divided by 120. 850 divided 120. So we get about 7 amps of current. I'll just write that as 7.1 amperes. Okay, so now we can find the resistance. The resistance is the potential difference divided by this current. So the resistance is the potential difference divided by the current. We have the potential difference, it's 120. We have the current now, it's I'll write this 7.08 amps. And then if we divide that, so I'm going to take 120 divided by this answer, and I get 16.9. So roughly 17, and then the unit is ohms. What the heck was that? Try that again. So those are some straightforward, simple questions, just kind of getting at the idea there. So what exactly is resistance? So resistance is just telling you, how easy can charge flow through. Like it's relating to the amount of energy that the charges are going to lose. So the lower the resistance, the less energy the charges will lose when they flow through the circuit. Or put it another way, the lower the resistance, the more current can flow. So resistance sort of restricts the current. The higher the resistance is, the less current you're going to be able to push through that material. So resistance is related both to the energy as well as to the current. So a higher resistance means more potential difference or more energy being lost at the same current. And then you can also say that a higher resistance means less current. And all those relationships can be seen right here. So if we have a lower current, that's when you have a greater resistance. And if you have if you lose more energy, that's because you have a greater resistance. So greater potential difference means more resistance, less current means more resistance. All those relationships are within Ohm's law. But remember, this doesn't work for every material. Let's talk a little bit more about why not. It is also known that resistance is affected by temperature, but the relationship is complex and difficult to model. So for this reason, we typically consider only the ideal situation, which is not real life, where the temperature of the conductor is held constant. Obviously, like the temperature is not going to be constant, right? Because like when you turn on something, when you run current through it, the wire, the material is going to get hotter. So we're saying like ignore that. Just imagine that like it's already been on for a while and the temperature is constant. Suggests a reason why resistance tends to increase with temperature. So back to our model up here, like our visual model of the electrons moving through the circuit. Why would resistance increase when the temperature of the material is greater? So if the temperature of the material is greater, these atoms are going to be oscillating more rapidly. And so if they're oscillating more rapidly and these electrons are flying past, imagine it's just oscillating, and an electron comes by, the electron could probably sneak past. But what if the atoms are going like this? And then the electron tries to sneak past, it's probably not going to be able to make it. So you can imagine that like the increased oscillations of the lattice atoms due to the higher temperature means it's more likely for the electrons to collide with the lattice atoms. Does that make sense, guys? Like, let me know what your thoughts are on that.
Yes.
So let's write that down. Insert text. Okay, so at higher temperatures, the lattice ions, I gotta remember to call them ions because I always try to call them atoms. The lattice ions oscillate more rapidly. Hence, collisions between the ions and electrons are more likely. This increases, or I should say decreases current and thus increases resistance. So that's the main idea. Is like when the temperature is higher. Remember, this is really complicated. Like we're drastically simplifying this, but generally speaking, the hotter a material is, the more difficult it'll be for charge to flow through it because it's more likely that those lattice atoms will collide. The opposite is also true. Imagine if you were to lower the temperature, there's actually a point where the temperature could get so low that these lattice ions are not even barely moving at all, and so the electrons don't suffer any collisions. And if that happens, you have a material called a superconductor. And so superconducting materials generally have this cutoff point where if you're below this temperature, there's no resistance in the material any longer. So as soon as the electric field gets that electron moving, that electron will never stop moving. It won't lose any energy, and you'll have zero potential difference across that wire if it's a superconducting material. Okay, question 5. Experiments show that 3 factors affect the resistance of a wire kept at constant temperature. So we're going to try to come up with an equation to calculate the resistance of a wire. Now, obviously, if you know the potential difference and you know the current, you can find the resistance, right? But we want to know, hey, what about the actual properties of the wire? So what are the actual physical properties of a wire that lead to its resistance? So rather than experimentally determining the resistance by measuring the current at different potential differences, let's instead think about the actual physical properties of the wire and try to determine the resistance from that. All right, so the first property we'll look at is the length of the wire. So imagine if you have a wire that's this long versus a wire that's this long. How will that affect the resistance? So if the length of the wire goes up, what will that do to the resistance? What do you guys think?
Increase resistance?
Tell us why you think that, Alberto.
Because the electrons have to flow farther.
And then what does that mean is more likely to happen to the electrons?
They'll collide.
Bingo, you got it. That's exactly right. So the longer the wire, the more likely the electrons are to have collisions. So a longer wire makes lattice, I'm just going to call it lattice collisions, much more likely. And if there's more collisions, there's more resistance, it's harder for the electrons to flow, and so that's going to give you a greater resistance. So if we want to write this out, we could say that R is directly proportional to L. Shorter wire, less resistance. Longer wire, more resistance. That makes sense. Longer wire makes lattice collisions much more likely. Okay, what about the cross-sectional area? So if we look at a wire that's this much space compared to a wire that's this much space, what will the wire do? So if we have we're looking at this area here. So what happens if we increase the cross-sectional area of the wire? What will that do to the resistance? This one's a little bit trickier. I'm trying to draw the lattice ions. The way I like to think about it is like, imagine this is like a one-lane road. There's only one road that cars can drive down, whereas this is a road with lots of lanes. So along which road will you be able to have a greater flow of traffic? The big or little one?
Big.
Bigger area.
The big one. So if you increase the area, it's actually easier to flow, which means the resistance actually goes
Down.
down. So we'd say that a larger area, larger area increases the amount of space charges can flow. So more space means more room, means less restriction. So there's less restriction. So if you had a really thin wire, you're not going to be able to get very high currents through that wire. You're going to have a really high resistance with a tiny wire. And so that's why with my car, for example, the wire that I have to plug my car into the wall with is giant. It's like this big. It's like huge. It's this ridiculously thick wire. And it's because it has to carry like 50 amps of current through it. So you're not going to be able to push 50 amps of current through a tiny wire. I mean, you might be able to, but that wire would probably melt. And so just for safety, they put this giant wire on the plug for my car. Okay, so we're going to say that resistance, therefore, is not direct to area, but it's actually inverse to the area. So we've got these two relationships, direct to length, inverse to area. We can combine those into one equation. So we can say that resistance is proportional to L over A. And we're going to define this symbol rho. So this is the Greek letter rho. It looks like that. It's kind of like a weird combination between like a P and a Q. So that's the Greek letter rho. And it's the constant of proportionality between these things. So we can write down that R is equal to rho L over A. And so rho is going to be a new quantity. And I like to introduce this as just kind of like a mathematical idea, because what the heck is rho? Well, rho is just some proportionality constant that depends on two things. It depends on the material that the conductor is made of and the temperature. So rho isn't really it's not like a physical, I mean, I guess it's kind of like a physical characteristic. It's basically like a characteristic of the material of the conductor and its temperature. So you could look up like what's the resistivity of copper? What's the resistivity of gold? Don't confuse resistivity with resistance. They're two completely different things. So resistivity is a material property, whereas resistance is this concept, is this idea of potential difference divided by current. So resistance is a completely different idea. The resistivity is just saying to you, you know, how roughly how hard is it for this, how well does this material carry charge, or how poorly does it carry it. It's just like a number that kind of tells you like how good of a conductor the material is. So the lower resistivity, the lower electric resistance there'll be. All right, what are the units of resistivity? So if we solve this equation for resistivity, which is this rho thing here, that's resistivity. So if we solve for rho, we'll get AR over L. So rho is equal to AR over L. Actually, I think it's usually written as RA. I'm going to change it. RA. Doesn't really matter. RA over L. So now if we look at the units, so units, the units are going to be units of resistance, which is ohms, times meters squared, so square meters, divided by length, which is meters. And so we can see, let me put these in parentheses so we don't think these are like physical quantities. And then we can notice that this one of those meters is going to cancel out. And so we get that the units of resistivity are ohm meters. So resistivity has units ohm meters. Ohm meter, an ohm meter, whatever that is. So yeah, and it's not ohms per meter, it's ohm meter. Okay, let's do an example problem, and then I'm done with this video. I know I'm running out of time here. Looks like I'm just about at the 30-minute mark. So I'm going to finish up this question and then end the video. All right, what we want to do is we want to calculate the length of a copper wire that has resistance of 5 ohms. So copper is a good conductor. I mean, you guys have all heard that. Copper is a really good conductor. We talked about it in a previous lesson because it has a high free electron density. There's lots of free electrons in copper. It's a good conductor. It can carry charge quite well. But we also have to consider the structure of the lattice atoms and how likely collisions are to occur when it flows through there. And so all of that together gets us this number of the resistivity of copper. So that's going to be not R, this is rho. It wants us to find the length. The diameter is 4 millimeters. So the diameter is 4 millimeters. That's going to let us find the area. And then it gives us the resistance, which is the electric resistance of 5 ohms. So we're saying, hey, how long does this copper wire have to be so that the resistance is 5 ohms? Remember the toaster, the resistance was 17 ohms. So what if we wanted to make a toaster out of copper wire? So how long would the copper wire need to be to make a toaster out of it? To have 17 ohms, well, whatever, 5 ohms is comparable to 17 ohms. All right, let's do this. So first up, we're going to need to do the area. We're going to have to find the area. So find the area. All right, so the first thing is we know that the area of a wire, area is pi r squared. But it didn't give us r, it gave us the diameter. So given that the diameter is 4 millimeters, what would the radius be?
I don't know. This is a hard one.
You guys know how this works. I'm pausing here because last year, or the seniors right now, when I gave this to them on their test, 90% of students missed this question. So I'm pausing here to make sure you guys know how to do this. It's not like I mean, it is trivial, but for some reason students mess it up.
It's 2.
Yeah, it's 2 milli, so times 10 negative 3. And I need to square that. So I'm going to grab my calculator. I'm going to do 2 milli. So 2 times 10 negative 3. I'm going to take that number and square it. And then take that number and multiply by pi. So pi r squared. And so there's my area. This is the cross-sectional area of the wire. The cross-sectional area of the wire is 1.26 times 10 to the negative 5 square meters. Okay, now that's not the answer to the question, but we're going to need it because our equation has area in it. And so just remember that what we're looking at here is the wire. So here's the wire. And we just found this area of the wire because we knew that the diameter of the wire was 4 millimeters. So we want to first find the area because it'll just make plugging into this equation a lot easier. Okay, next, we are trying to calculate the length, which means we need to solve this equation, or this one, whatever one you want to use. We have to solve it for L. So we're going to multiply both sides by A and then divide both sides by the resistivity. So we get that L is equal to resistance times cross-sectional area divided by the resistivity. And all of this is stuff that we have now. We know the resistance is 5 ohms. We found the area just now. It was 1.26 times 10 negative 5 square meters. And then I'm going to divide by the resistivity of copper, which was given over here, 1.68 times 10 to the negative 8. 0.68 times 10 to the negative 8. And that's an ohm meter. So notice why the units have to be ohm meters. It's so that these ohms will cancel out. One of these meters will cancel out. And that way our length will just be in meters. And so we write the units there because this is showing us that it worked. We didn't have an algebra error. If you don't put the units down and don't check it out and don't get meters as your answer, you know you screwed up the algebra. So the units are self-correcting. So you always want to try to consider the units when you're solving out problems. Okay, so 5 times 1.26 times 10 to the negative 5. I think I just had that in my calculator and I just cleared the screen. I should have been paying more attention. And then 1.68 times 10 to the negative 8. So I get this length, 3,750. So a copper wire would need to be 3,750 meters long in order to have a 5 ohm resistance. So we'll say, let's say there's 2 sig figs. I think, let me check. So 1.68, 5.00. No, we have 3 sig figs, so we're fine. So we can say 3,750 meters and we're good to go. So think about that for a second. Copper is such a good conductor that if you wanted to just have a 5 ohm resistance, you would need like 3,750 meters of copper wire in order to have a 5 ohm resistance. Typically, when we're solving problems, when you're like connecting wires to a lamp, like we did in the last question, your wires are like, what, maybe 20 centimeters long? Way less than this. So generally, with a copper wire, you can just straight up ignore the resistance, and we will generally say that, yeah, the resistance of copper leads, like when you're building small circuits, the resistance is nearly zero. Okay, that's it for this video, guys. So now go to Google Classroom, I'll pull up the assignment. There are some questions for you to answer, and I'll show you the solutions to those in part 2 of this video. Have a great day.